Hi everyone, my name is Matt. I'm going to be talking to you today on the impact of lossy image and video compression on the performance of deep convolutional neural network architectures. I've worked on this with my colleague Amir and my supervisor Toby Breckon under Durham University. So what do I mean by lossy compression? Here we're talking about the removal of redundant information such that the difference is imperceptible to the human eye. Common algorithms to do this are JPEG for image and H.264 for video compression. Now, if we're presenting compressed images to networks, i.e. images with less information in them, we might expect that the networks perform less well. But to what extent is this the case? So to address this challenge, we have 5 networks spanning 5 different domains, and with 2 goals in mind. Firstly, if we take a pre-trained, out-of-the-box network, how well does it perform in the face of compression? The second challenge is, if we retrain the network on compressed imagery, does it perform better? So first up, we have a segnet to deal with pixel-wise segmentation, i.e. attributing each pixel in an image its corresponding class. So segnet, it's important to note, is an encoder-decoder architecture, otherwise known as bow tie architecture, and it will become clear why later why this is important. So in the top left, we have an image that is being compressed with a JPEG compression level of 10. That means that it has been reduced to 10% of its original size. And as you can see, compression artifacts are beginning to creep in, especially on the road, and the network is picking up on this, as you can see at the bottom of the image in the forefront. Nevertheless, overall, segnet actually performs quite well in the face of compression. This is in fact one of the images that it has performed worst on. And as you can see by the accuracy in the mean intersection over union, before retraining the network, we can achieve compression rates of almost 15% with negligible loss in performance. By retraining the network, we can get even lower. We can achieve compression rate of 5%. Next up, we have GAN. So GAN are often associated with image reconstruction. And so, of course, if we pass it a compressed low-quality image, we will most likely get a low-quality image out. Therefore, we need a task decoupled from reconstructing high-quality output. Therefore, we use depth estimation. And so, again, looking at the results, this time lower is better. Before retraining the GAN, we can achieve good results with compression rate as low as 15%. After retraining, we can once again get it down to as low as 5%. Thirdly, we have object detection and classification. And to do this, we're using the Detectron faster RCNN implementation. So before retraining, we're able to compress images by as much as 50% without loss in performance. And after retraining, we can get that down to as low as 10%. One thing that's interesting to note, however, is that while the classification accuracy and precision may change during compression, generally the confidence does not. Fourthly, we have human pose estimation, and here we're using the open pose network to compute and overlay the skeletal structure of humans. And once again, before retraining, we can achieve a compression rate as much as 50% without loss in performance. And after retraining, we can get that down to as low as 15%. Finally, in the video domain, we have human action recognition. And to do this, we're using a 2-stream network. Unlike, say, Siamese twins, where training of one stream impacts the training of another stream, here we train the 2 streams entirely separately. One stream is dealing with spatial, i.e. frame by frame. Another stream is dealing with motion, i.e. receiving several frames at once. And so, before compression, the spatial stream performs quite well, the motion stream far less well. Overall, there is a good, or we can compress to about 15%. After retraining, the results in fact get worse. Spatial is resilient, motion is rendered almost unable to learn by compressed imagery. Nevertheless, overall, we can achieve compression rate around about 15%. So overall, what can we conclude? We can afford to safely compress all our data by as much as 15% of the original size across all domains and receive a negligible performance in our networks. So to reiterate, if we think about all the data sitting on our hard drives, we can reduce that storage capacity to as much as 15%, and we probably won't notice on our networks all that much. Secondly, we note that the networks that employ a decoder subnetwork are the most resilient, and we posit that this is because the upsampling within the pooling layers of the decoder network are responsible for the resilience to compression.